Thanks, everyone. Yeah, as Adam said, I work with him at Weaviate, and today I'm going to give just a very short slide deck. We're going to breeze through it. Oh, I'm going to try and keep it 10 minutes. Nice. Thanks, man. Okay. So you're going to get my 6-hour workshop in 10 minutes. Really going to go fast. Okay, what we're going to do is I'm going to talk a little bit through what Weaviate does. We're a vector database, how you can use it, as well as some new agents one new agent in particular that we've developed that abstracts out a lot of the work and can cut down creating a RAG system to something that can take 300 lines of code down to about 30. It's really, really impressive, as well as I'm going to talk a little bit about chunking your data before you put it into your vector index, which will make sense into your vector database, which will make sense here in a minute. And then I'm going to talk a little bit about DLT Hub, especially since they can't be here. I've integrated it into a notebook that I'll share with you guys, so if you want, you can build on it for the hackathon. Really quickly, what is a vector database? A vector database is a database that stores semantic information so that we can use it for querying, and we don't have to use keywords. We can actually use the context of an item to use it to generate really useful text from a generative AI model. This is a very simple example of a vector database. So a vector database essentially places objects in multidimensional space close together if they are closely related semantically. So if you see here, dog and wolf are pretty close together. They are both four-legged mammals of the genus Canis. We also see cat relatively close, but not quite as close as wolf and dog. Cat is another four-legged mammal, related to dog and wolf, but not as closely related to the two as they are to each other. If we look on the other side, we have apple and banana, which are both fruits. Because they're not four-legged mammals, they're further apart in this multidimensional space. But because apple and banana are both fruits, they're close together. So the idea is we can measure how similar objects are based on proximity in the database. And this makes it really easy to be able to query because we could take something like the word orange, throw it in this database, and we're going to see that it shows up next to banana and apple. So if we were querying with orange and saying, like, give me some things that are similar to orange, we're going to return banana and apple because the vector or the model is going to know, the embedding model, the thing that we're using to put into this vector space, when we query with information, it's going to pull the things that are closest to it to give us some context around the object. This is really useful when we're querying for information. So for instance, if we wanted to get some really specific information from a book, or, as we're going to see in this presentation, a bunch of scientific articles. We want to ask some really hard questions and get some really good data back in response. What we could do is we could send a generative AI model everything we have. We could send it a whole book. We could send it all of our papers that we want it to read. The problem is that's going to fill up your context window pretty quickly. So RAG systems, as you guys have probably all heard of by now, are a really great way for you to pull really high quality information from a whole bunch of text. Or maybe you want to query video or images or sound. These can all be stored in a vector database using embedding models, which is what, if you decide to use this notebook, you're going to build today. Now, one of the big questions about vectorizing data, if you're going to put this into a vector database, is how do you split it up? So I just gave a little bit of a preview. If you want to search for information from a book or from a whole library of scientific articles, you don't want to put an entire book as one object in a vector database. Because if you ask a question that has to do with that book, you're stuck with the same problem. It's going to return the entire book to you in that context. So prior to storing your information in a vector database, you have to break it up into pieces. And this is really important to me. I'm a research scientist at heart, as well as a data scientist. And if anyone's ever done data cleaning, you know that that's kind of the worst part of any type of data science project, right? Nobody likes to do the cleaning, so we usually make the new guy do it. In this notebook, I've already done it for you, so you don't have to worry about it. we're going to be working with some scientific articles for this particular project that have to do with space medicine. Going in outer space, as it turns out, is really hard on the human body. And it can have some unknown implications, especially when astronauts return to space. So what I've done is I've taken a myriad of space health articles, and I've linked them in the notebook that we can pull from, and we're going to do some chunking. And research articles are a really great example for chunking because research articles are generally divided into different sections. You have introductions, materials and methods, results, conclusions, discussion, that type of thing. So you can actually take these articles and break them up into sections. And if those sections are too long, you can break those sections up into subsections based on paragraph or sentence, or even a certain number of tokens if you want to. Ultimately, the object is you take a breadth of information and you break it into pieces that will work for you to put them in a vector database, and a generative AI model can take those vectors and make sense of them. And that's exactly what we're going to be doing today. So in a nutshell, the way that a RAG system works is you have a bunch of data, whether it be documents or it be scientific articles, it be images, it be videos, and you break them into pieces that make semantic sense. You then use what we call an embedding model, which takes all of that information and turns it into vectors, which are simply numerical representations of data. And it's going to dump them into our vector database. The next step is you take your query and you vectorize it as well using the same embedding model. So that way, when you drop that query into the vector database, you simply grab the vectors that are around it. And you can say with a certain degree of certainty, if you use the same embedding model, that those vectors that are near your query are very related to your query. Or at the very least, they're the most related objects in your vector database to your query. Once you've gathered those objects, you can send those to an LLM. And very simply, it takes all of that context, it takes your original query, and it gives you something in return that makes sense. It's a really great way to cut a lot of work out of a system, especially if you are wanting to know something from a group of scientific articles or a book. You don't have to read 100 articles. You can have the vector database and the AI essentially do that for you. Now, what I want to talk about is Weaviate's query agent, because what the query agent does is it abstracts a lot of these steps out of the process. Like I said, it can take something that can take over 300 lines of code and reduce it to 30 lines of code. Generally, each one of these steps is a separate API call. And depending on what you're using for your embedding model, what you're using for your generative AI, ChatGPT, Cohere, whatever it might be, or Claude, as well as generating your prompt templates with the vectors that you pulled out that are similar to your query. This can be 3 separate API calls. With the query agents, it reduces it to 1. You can do all of these things with 1 API call through Weaviate's query agent. It makes it super simple. Additionally, in the notebook, for the chunking, that could be a separate API call as well, or you could build some complex code that will go through and search for your sections and divide them up however you ask it for. In this notebook I'm going to show you, or that we're going to send out, you can actually use Llama Index to do a lot of the heavy lifting for you. As a little bonus, because DLT Hub was a part of this hack night, DLT Hub will actually go through and it will look at your chunks to make sure that everything was chunked correctly, and it will give you a report that will tell you the details of those chunks. It's going to be a lot more work or a lot more output than you need for this notebook, but when you're running something in production, it's really handy to have something that's actually going through and validating all of your data that you're putting in, so that if you are seeing bad responses, you can go back and you can find out where those are coming from. There's this old saying in data science, which is garbage in, garbage out. And if you put bad data into anything, you're going to end up with bad data as a result. There's some really other really cool stuff that the query agent can do, which I'm just going to briefly touch on. It can actually do aggregation, so it can do math. It also can go through and read your metadata. So it prevents you from having to add an extra filtering step into your query if you are wanting something that isn't actually vectorized and is part of the metadata itself. Okay, so on to the notebook. I'm just going to breeze through this. You guys will have access to this. So in the notebook, there's a little bit of background information, as well as links to the slide deck if you're interested, and the repo, and the journal articles themselves. It's just basically installing some libraries. Here are the medical science links, some chunking functions that essentially will wrangle your data for you and allow you to parse through these documents so that you can pull out all the sections so that when you send it to the chunker, it will already be divvied up for you. Pretty basic stuff. I imagine most of the people in this room are much better coders than I am, so I don't think this will require much attention or explanation, and there are a lot of comments in here that you can read through. The thing that I do want to point out in this notebook, if you choose to use it, is I have two different options here. The first is you can chunk without a DLT pipeline, which means you're just trusting that your data is chunked correctly before you put it in your database. Alternatively, you can build a pipeline with DLT, which will give you a nice, very verbose output. Again, not super useful for this workbook, but if you're thinking about putting something into production with a RAG system, having this extra check in the mix is super helpful because it makes it really easy for you to go back and find out when something goes wrong. Lastly, this is the part, if anyone's going to have any issues with this notebook, this is probably where it's going to be. Setting up all your API keys, or your API key and your REST endpoint from Weaviate, just because you're going to have to go in and create an account, a free account, and a free sandbox cluster. It's all free. And there are detailed instructions linked at the beginning of the notebook on how to do this. Lastly, for Weaviate to work, you'll need to create a collection, which is essentially a database. I'm sorry, a data table within your cluster, which is the database. And then finally, we will upload all of our chunks, so that chunks of data to the database. It will do all the vectorizing and embedding for you, so it will dump those into a vector database that you've created in your cluster. And then you can just very simply query it with the query agent. It doesn't require any setup other than just telling it what collection you've created that you want to query, and then asking it the question that you would like an answer to. Super basic, super straightforward, and yeah. It's a really great exercise if you're interested in RAG systems. Okay, thank you very much. Any questions? I'm going to have Andrew or Adam drop it in Luma. So it should be with the other materials for the hack night. Nice, nice. Awesome. Thank you all so much. Oh, one more. Oh, yes. Ooh, great question. So the question is, what if we are trying to pull semantic meaning from something that is not as cut and dry as cat and dog, fruit versus mammal, right?
What if like the same entity could have a couple of meanings in different contexts?
Oh, like the same word can have different meanings in different contexts? Okay, that's a really great question. So chances are we won't be vectoring just one word at a time, but that's what I showed on the screen. So this is an excellent thing to talk about a little bit. So chunking is really important. And this is one of the reasons that I wanted to address it, because yeah, if you're putting in one word at a time, like we have a lot of homonyms in the English language. So that's not going to be enough context to be able to separate those two out. Because if we use the word, and now that I'm up here, I can't think of any. I don't know, anybody have any? Orange. Orange? Okay. Could be a color, could be a fruit. Great one. Oh, thank you so much. You saved me. Yeah. So if we put that in there, the embedding model is probably going to choose one of those things. And it depends on the training which one of those meanings it's going to choose. So ideally, we would have more context around that. Instead of just having the word orange, we would have it used in a sentence. So we would say the fat cat was orange versus orange tree. And that's one of the things to really be thinking about when you vectorize your data, or when you chunk your data, is so that you don't run into issues like that. Most of the time, you're not going to have single word chunks. It may be appropriate in some instances. I can't really think of any off the top of my head. But generally speaking, you're going to be chunking at least a sentence, maybe a paragraph. Depending on what you're chunking, it may be a chapter. Great question. Any other questions? Yes, sir. I'm sorry? Postgres? Yes. So that's another great question. I actually worked on a project recently where I did this, where you can take it depends on the size of the database or data table that you're trying to vectorize. If it's a small data table, you can vectorize the whole thing, and it will actually hold the semantic meaning of the objects in the database or the data table itself. Or if it's a large database and you have a lot of different columns, you can actually vectorize by column. And the metadata is conserved in the collection within Weaviate, so it can link those things together even if they're not in the same vector. Another great question. Yes?
Does it have any linguistic limitations? So like the example with the orange and orange is easy in the English context, but the lexification of words that mean the same thing in separate languages would have just this
Ooh, great question.
meaning.
Yeah.
So how does it deal with that, or is there more training just on the English language and not the other ones right now?
That's a great question. So the question is, what if you have words that have very similar meaning, or they have different meanings in different languages? So how do we overcome the language obstacle? That's a really great question. It's something that is overcome through the type of embedding model that you can use. So not all embedding models are created equal. For instance, OpenAI has an embedding model, Ada 2, which is trained on like everything. It's like the vastness of the world and the internet. So that's really great for a general query system. But if you want something that's very language sensitive, you'd want to use something like Cohere, because their embedding models are really great with different languages because they've been trained on more languages than just English.
I just want to throw out, going after the language helps a lot from a cultural perspective when analyzing data, so that's why I was
Yeah, that's a great point. He's pointing out that the type of language you're using culturally can have different words can have different meanings, right? Like,
same words can have different, but
sorry, the same words can have different meanings. Yeah, culturally. That's a great point. Yes, up here.
I'm going to kick you off after this one.
Cool. Ooh, great question. How do you use it to do like data analysis for financials, right? Great. So you can vectorize those data tables. And it comes down to really the size of the data table, so how many columns you have. If it's a relatively small data table, let's say you have like, I don't know, 500 rows and like 12 columns. That you could probably just vectorize that one data table because it will conserve a lot of the information in there. But when you start looking at huge data tables, like maybe you have 100 columns and like 5,000 rows, you might want to chunk it so that each column is its own vector, because it will still conserve within the metadata the relationships between those columns in your data table. It just might not make sense when it gets so big that you do it all at once. And that requires a little bit of playing with it, finagling. If you guys have more questions, I'll be here walking around. If you need help with the notebook, if you just have questions about embedding in general, hit me up. I'm here to help. Thank you. Nice to talk to you.